In this video, we're going to talk about series. So let's start with a specific example here and see the idea of what we're trying to get at that's motivating the idea of series. So certainly we know that the fraction 1/9 is 1 repeating, so 0.11111 forever. So another way we could write this, instead of just writing the 11111 forever, is to write the 1/9 as 0.1. That'll get you your first decimal place. The 0.01, that'll get you your second decimal place. And then plus 0.001, that'll get you the third, and so on down the line. So we can think of this 0.1111 and so on as being this infinitely long sum. So the thing on the right-hand side is an example of what we refer to as an infinite series. So more generally, when we have this a1 plus a2 out to an and so on, we'll write it as the sum from 1 to infinity of a sub n. What we're interested in for an infinite series or an infinite sum, we want to know if this thing converges to a finite value. We did that kind of. It's a similar concept, but not exactly the same, as when we did integration, when we did Riemann sums, right? We were hoping that that Riemann sum would converge to a finite value. And you're really doing, in some sense, an infinite sum, right? You took a limit of a sum idea. All right, so to figure out whether or not this thing converges, we're going to use what's referred to as the sequence of partial sums. So we'll set the first partial sum equal just this, the first term. Now notice the second partial sum, though, however, is the first term plus the second term. So the third one would be the first plus the second plus the third. So we're making a new sequence here, okay? So the nth partial sum would be the sum of the first n terms. So this is how we're going to determine whether or not a series converges. We'll say that the series converges if the sequence of partial sums converges to a number. And we'll say the series diverges if the sequence of partial sums diverges. Now, it's very, very, very tempting to say that the series converged because the sequence here, this a sub n's did. That is 100% false, okay? Do not say that the series converged because the sequence did, right? There has to be some very, very special things going on in order for the series to converge. These are just numbers. Just because the numbers settle down and go to some value has nothing to say about what's going to go on with the series, whether or not it settles down to one value. Let me give you a specific example. What if all of your sequence terms were 1? Well, that certainly converges to 1, right? You just have a constant sequence, 1, 1, 1, 1, 1, and so on. However, if you add a bunch of ones together, that's not going to converge. That's going to go off to infinity, okay? So make sure that you understand the difference between sequence converging, having a limit of a sequence, versus a series converging, a sum going to a finite value. Okay, it's a big deal. All right, let's go back to that original example. Notice that our first decimal place really is just 1/10. Second one is 1/100th, or 1/10 squared. This one's 1/10 cubed, and so on. So we can write that this series, this special type of, this particular infinite series converges. It converges to a 9th, because that's what that's how we got the series to begin with. We knew that 1/9 was that repeating decimal. All right, so what's the sequence of partial sums then? Well, it's just first partial sum is just the first term. Second partial sum is the sum of the first 2 terms. Third one is the sum of the first 3 terms. So on down the line. Your sequence of partial sums in this case will be 0 with n ones behind it, because we're adding those n decimal places at each step. We know that sequence converges to a 9th, like we said, so that series has a value of 1/9. All right, so specific example, this is one that pops up in lots of applications, especially if you go on to doing anything with probability, for example. Geometric series are very, very important examples. So for any constant r, the series that starts at 0, goes off to infinity of r to the n, we refer to that as a geometric series. Oops. So let's start with, assume first that the r is not equal to 1. We just discussed a minute ago what happens if r is equal to 1. This thing does not converge. You get an infinite sum. Okay. So let's assume for argument's sake that it's not equal to 1. All right, let's look at our sequence of partial sums. The 0 term, the 0th partial sum, if you will, is just that 0th term, it's 1. First partial sum is what you get when you plug in 0 and then plug in 1 and add it together, so you get 1 plus r. Note that 1 plus r is the same thing as 1 minus r squared over 1 minus r. Second partial sum, plug in 0, plug in 1, plug in 2, add them together. 1 plus r squared. Again, check. This is the same thing as 1 minus r cubed over 1 minus r. In general, if you've got 1 plus r squared plus r to the n, which would be the nth partial sum, and again here, this is plug in 0, plug in 1, plug in 2, all the way up to plug in n, right? In general, if you've got this sum, it's 1 minus r to the n plus 1 over 1 minus r. This is why I definitely wanted to make sure I said r is not equal to 1, right? You can't plug in 1 in the denominator. All right. So notice that if I want to take the limit of the sequence of partial sums, I want to take the limit of this expression on the right-hand side. Well, the only thing that even has an n in it is this piece up here, that second term in the numerator. So if I can compute the limit of r to the n plus 1, then I know what my limit of my s of n is. This is a limit we've talked about before. We already know that this limit exists and is 0 when the absolute value of r is less than 1, and does not exist if absolute value of r is greater than 1 or if it's equal to negative 1. And I mentioned before that if r equals 1, then that series certainly diverges. So what do we have? Well, if our absolute value of r is less than 1, then the sum of the geometric series is 1 over 1 minus r, because we know that this limit right here is 0 if the absolute value is less than 1. And if the absolute value is greater than or equal to 1, then we've exhausted all those possibilities. If the absolute value is greater than 1, greater than or equal to 1, I should say, the series diverges. So let's see if we can do an example here of finding a sum of a geometric series if it actually converges. So we've got the sum from 1 to infinity of 7/9 to the n plus 3 minus 3/5 to the 2n. All right. Well, first thing we're going to do is we're going to split up our series over that minus sign. Now we have to be a little bit careful. This only works if both series converge. Okay? If even one of the series diverges, you can't do that split up. But notice that we can kind of see what the r values here, right? We see the 7/9. This one we see a 3/5, and we're going to end up squaring it with that 2 there. So I think we're okay as far as converging goes. It looks like those r values have absolute values less than 1. Okay, so now remember from the previous slide, the series started at 0 for our formula. These series start at 1. So we're going to do something that's referred to as re-indexing. If I want this series to start at 0 instead of 1, then I'm going to need to add 1 to my n, right? Because when I plug in 0, I still want to get 1 out. So notice here I went from 1 to 0. I subtracted 1. I better add 1 up where the n is to keep things balanced out, if you will. And then the same idea here, okay? This is what's referred to as re-indexing, right? Drop this down 1, I better increase my n on the inside by 1, because I want to make sure it starts in the same place. I want to make sure I keep things equal. I need to balance things out. All right, this one is n plus 4. I'm going to rewrite that as 7/9 to the n times 7/9 to the 4th. The reason is, of course, remember the formula was r to the n. Okay. Same thing over here. Distribute the 2 and split off the 3/5 squared. Now, this is a sum, and this is a constant. So just using basic algebra principles, if you will, we're just going to take these constants and we're going to pull them out in front. We're just factoring it out. Okay. The reason why that works, of course, again, is because really these are, when we think about how the convergence works, it's a sequence of partial sums, and we know that we can take constants out of limits. So that's the real technical reason why it works. But again, it's a sum. We've got a constant. We're just factoring out the constant. Now we've got sum starts at 0, r to the n in both cases. So we use our 1 over 1 minus r formulas for that. And if you go through all the nasty arithmetic, you'll get that nasty fraction that no one really cares about. All right, so let's talk about some facts about series. To start off with, let's suppose that both of the series converge, just like we mentioned in the previous one, right? The first series sum goes to L, the second one goes to M. By the way, you'll see this a lot where the indices here are not listed explicitly because people are lazy, essentially. But well, as you go farther and farther along with series, what you're really interested in is whether they converge or diverge, not what the explicit value is. So the fact that we're dropping off the indices really only is changing what the number would be, but all we really care about is whether the number actually exists. All right, we used this one in the previous example. We can break the series up over sums, and that should be a minus in there too to keep with the plus or minus idea. We can pull constants out. We did that in the previous example as well. Turns out, of course, that if the series converges, then the terms have to go to 0. But just, again, I got to harp on this. Just because the terms go to 0 does not mean the series converges. Okay? Doesn't tell you anything. All it tells you is that if it doesn't go to 0, then the series has to diverge. That's all it tells you. That was what we refer to as the nth term test for divergence. You can never, ever, 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 ever show that a series converges by looking at the nth term test. It's only diverges by the nth term test. All right, so let's look at a specific example. Let's see if this series inverse tangent of n plus 5 over n plus 6 converges. All right, so we're going to take the limit of the terms. Well, a limit of inverse tangent of that, well, I can move the limit inside the function. No issues there. This is essentially n over n. That limit's going to be 1, and inverse tangent of 1 is not 0. It's pi over 4. Okay? These terms do not go to 0. Basically what this says is that eventually you're adding pi over 4 to itself infinitely many times. That's not going to go to a finite number. Okay? So since the limit wasn't 0, the series must diverge. Okay. Now again, you can only use this for divergence. If you tell me that the series converges because the nth term goes to 0, that's no credit. It's false. You can't tell that from that. All right. So let's look at another one here. This is the last example we'll do for this video. Series n equals 2 to infinity if 4 over n squared plus 6n plus 8 converges, whether or not it does, and then find a sum. All right, now notice these terms will go to 0, but it doesn't tell you squat. You've got to do more work to see if it converges or not. All right, the more work in this case is going to be, we're going to start with partial fractions. Notice that your denominator factors as n plus 2 times n plus 4. So partial fraction decomposition would be a over n plus 2, b over n plus 4. Clear your fractions. Plug in your good values for n. If n is negative 2, you get 4 equals 2a, so a is 2. N equals negative 4 to kill that term off. 4 equals negative 2b gives you b is negative 2. So I can replace that expression on the inside with 2 over n plus 2 minus 2 over n plus 4. Now let's analyze the sequence of partial sums. Okay, plug in 2 in this case. Notice that this series starts at 2. So it's going 2 in here, so you get not 1. This should be 1/2 here. So I've got the wrong number here. This should be a 1/2, not a 1. So I've got the wrong number here. So this should be 2/4 minus 2/6. So this should not be a 1. This should be a 1/2 here. My apologies. I'm not going to simplify this though. All right. So for S3, then the next one would be plug in 3 for n. So you would have 2 over 5 minus 2 over 7 for your second term. I would add it to the first term. And again, this is a 1/2 here, not a 1. My apologies. Okay. Again, not going to simplify it. Let's do the next one. Here's the first term. Again, it should be a 1/2, not a 1. Here's your second term, or I guess technically this is the second term, third term. This is the next term. Plug in 4, you get 2 over 6 minus 2 over 8. Notice something happens. The 2 over 6 cancels in those two terms. So when those cancel, you should get a 1/2 plus 2/5, and then minus 2/7 minus 2/8. Let's do one more. Oops. Let's do one more. First term, again, should be a half. Second term, third term. Now when you plug in 5, 2 sevenths minus 2 ninths. Again, the 2 sixths goes away and the 2 sevenths go away. You're left with a 1/2 plus 2 fifths minus 2 eighths minus 2 ninths. All right, so in general, what's going on? Well, you always get the 1/2 and you always get the 2 fifths. That never went away, right? Those are all, and again, this is a 1/2, not a 1. Now what goes in the next one? Look at your denominators. Okay, for 4, you had 7 and 8. For 5, you had 8 and 9. So in general, for n, you should have n plus 3 and n plus 4. Now look at your limit. This wouldn't be 7 fifths. This would be a half, which is 5 tenths, plus 2 fifths, which is 4 tenths. So it should be 9 tenths, not 7 fifths. So the limit is 9 tenths. So if you're writing this down, this should be a 9 tenths, not a 7 fifths. So the series must converge to 9 tenths. Okay? Because these two terms both go to 0. As n gets really, really big, those two terms go up to 0. Okay? This is what we refer to as a telescoping sum.